This presentation is about the basic principles of heat pumps. It deals with thermodynamics, efficiency, and energy consumption. Let's think about a heat pump that is located outside a house and collects the heat of the ambient air. And we need to transport this heat from the ambient air inside the house to heat the house. How does this work? We have a collector that collects the heat from the cold environment, that is the air, ground or groundwater. This heat is then collected further with a heat exchanger and conducted to the cooling cycle. The cooling cycle contains a refrigerant. This refrigerant, that is a liquid that evaporates if it takes up heat. Evaporates, then it is conducted to a compressor, and then the gas is compressed. And by this compression we put energy into the gas, and also due to the special feature of the gas heats up a lot during this compression. And then the hot gas is conducted to another heat exchanger where the heat is extracted and conducted into heating for the house. That is the boiler of the house used to heat the house. And then during this process, when it releases the heat, the refrigerant condensates. And then after condensation, it is conducted to an expansion valve. And then as a gas, it can be expanded to lower pressure and higher volume, and during this process the gas cools down a lot. It is also a special feature of the gas that it cools down a lot, and then when it's cold it is conducted further to the cooling cycle where it can collect more heat from the environment because the gas is colder than the outside environment. And then the cycle starts from new and runs in a circle and transports heat from outside to inside. Let's further think about the efficiency of the heat pump. The efficiency of the heat pump depends on the temperature difference between inside and outside. The desired inside temperature. The more heat to be transferred, the more electricity we need. As an estimation, for 100% heat generated inside the house, we need 20 to 30% of electricity. The heat transfer rate from the heat pump can be expressed as the heat of the hot reservoir equals the heat of the cold reservoir plus the work we put into the system, for example by the compression of the gas and transport of the gas. The coefficient of performance can then be calculated and is a measure of the efficiency of a heat pump and is defined as the ratio of heat output to work input. The maximum theoretical efficiency of a heat pump operating between two temperature reservoirs can be calculated using the Carnot efficiency. It is calculated by dividing the temperature of the hot reservoir divided by the difference of the temperature of the hot reservoir minus the temperature of the cold reservoir. The temperatures are taken as the absolute temperatures in Kelvin. For example, the outside temperature in winter is 0 degrees C, which corresponds to 233 Kelvin. The inside temperature of the heating of the boiler is 50 degrees C, which is 323 Kelvin. The coefficient of performance is then calculated by dividing 323 by the difference of the two temperatures, and this is about 6.5. And this is a factor which is correlated to the electricity. That means that we obtain 6.4 times more heat than electricity needed to transport the heat. And this is a very high value. Let's further explore the efficiency. For that, we can plot the efficiency as a function of the temperature difference between inside and outside. And if we use the formula explained above, we get the theoretical efficiency. And the lower the difference of inside and outside, the higher is the theoretical efficiency. It is very high if the temperature difference is small, but it gets lower if we need to get a very high temperature difference between inside and outside. Unfortunately, in reality, we have further losses in the process. For example, we have to turn the radiator of the heat pump, and we have also some heat dissipation, maybe not perfect isolation and kind of these things. So we have further losses, and by experience we have to divide the theoretical efficiency by a factor of 2, and then we get a real efficiency of the heat pump, which is shown here as the orange curve. Practically, we can assume 30 to 40% of the heat required to run the house has to be provided by the electricity. So this is the operating area, which is marked, so we have to obtain the temperature difference between 13 and 15 degrees C. The energy consumption can then practically be calculated for a house in northern Germany. A typical value for a house is that we need 123 kilowatt hours per square meter per year as a normal value. That means for a house with a size of 130 square meters, this corresponds to an energy per year of 16,000 kilowatt hours. If we need 33% of electricity to provide this quantity of heat by a heat pump to transport the heat from outside to inside, this would result to 5,333 kilowatt hours we have to put into this system over the year. With a price of 37 cents per kilowatt hour of electricity, this results in €1,973 we have to spend for the year. If we use gas instead to heat the house, we can calculate with a price of 13 cents per kilowatt hour, and we obtain amount of €2,080 per year. So this is only slightly higher than the cost we have for the electricity we need for the heat engine. So practically we can assume only a slightly lower cost for the application of a heat pump. However, heat pumps can be very useful in combination with solar cells and energy storage, because then we would be able to collect the energy for the electricity for free. Thank you for your attention.